In this video, we're going to talk about data distributions and look at the shape of a data distribution, the shape of some sort of data graph, and see how we can describe what it looks like, basically. To start off with, the data distribution just means how is the data distributed? So, like, where are you putting the data? Where is it distributed? So basically, like, what is the shape here? Take a second and think about some similarities and differences between all of these graphs here. And basically, we're going to come up with words to describe the different things you may be noticing. All right, so we're going to talk about these four things. These are different ways you might describe the shape of a data distribution. Symmetry, skew, how many peaks it has, and uniformity. So let's get into symmetry first. You probably are familiar with this word. Symmetry just means it's the same on both sides. It's like a mirror image. I could draw a line straight down the middle, and it would be the same on both sides. If I folded it, it would be like right on itself. A symmetric distribution is just split right in half. And this is also symmetric because it's the same on both sides, and this one's also symmetric. It's the same on both sides. If it's not symmetric, it's called non-symmetric or asymmetric sometimes. All right, the opposite of symmetric data is skewed data. Skewed just means it's like pushed to one side or the other. So this data is kind of all pushed to the right. Like most of the data is over here on the right. We call this skewed left. So it actually goes with, sometimes this is called the tail because it kind of looks like a tail. You've got a few data points kind of straggling over here on the low end, maybe even some outliers. So this is called skewed left because the tail is on the left. Most of the data is actually on the right. This one is called skewed right because the tail is on the right. Most of the data is on the left. Here's an example of what that looks like with box and whisker plots. So when your data is symmetric, your box and whisker plot's also going to be symmetric. However, if the data is skewed right, your box and whisker are going to be a little longer. This might even be a little longer on the right. Or if it's skewed left, your box and whisker on the left are usually a little wider. That's because it's going to take more of this data to make up 25%. Whereas like this 25% right here, it's only going to take a couple bars. Whereas like this is going to take a wider area to make up 25% of the data. All right, so let's talk about the next one. To start off with, the mode of this data distribution is 39. It's the mode, it's the most often. This one has two modes, here and here. They may not be exactly the same, but they're both kind of mode-like. They're both kind of the highest point. So, when we talk about a graph like this, we could describe the number of peaks that it has. And we use this actually doing the mode. So, if a graph has one peak, we call it unimodal. If it has two peaks, we call it bimodal because it has two modes. Just by the way, sometimes they aren't exactly the mode. As long as it has two peaks, we call it bimodal. So maybe your data looks like this, and like clearly that one's the mode, not that one, but since it still has two clear peaks, we still call it bimodal. It doesn't have to be symmetric, like this one's also unimodal because it has one peak. This one is bimodal, it has two peaks. All right, and the last thing I want to mention is uniformity. This is when there are no clear peaks. That's when the data is basically all the same. It's just flat across the top. It's uniform. The word uniform means all the same. Like when people wear uniforms, they all look the same. Note that in the real world, it's probably not going to be perfectly uniform. Like this is probably more like what you'll see in the real world with real world data. But we would still call this uniform because it's pretty close to flat across the top. All right, I do want to mention this as well. Anytime you have a data set that is symmetric and unimodal, so one peak, that is called, you may have heard, a bell curve, and that's what this is. It looks like a bell. The official name is a normal distribution, just kind of, it's distributed normally. Most of the data is here in the middle. You've got a few low and then a couple really low, and then a few high and then just a couple really high. So that's called a bell curve or a normal distribution. Here's a few normal distribution jokes. Okay, just once again, to get back to the box and whisker plots, these two look pretty similar. They have the same min, max, and median, and they're both symmetric. The only real difference is that this one has a couple of outliers, this one doesn't, and this one has a very smaller interquartile range. This one has a slightly bigger interquartile range. So here are the histograms that would go with these. This one right here is actually uniform data because it's flat across the top. Every 25% of your data is going to be exactly the same. That's why each of these are the same width. It's because each 25% is the same. Whereas this one, more of the data is there in the center. And so that's why the middle 50% box here is kind of squished together. It's because it doesn't take that much to get 50% of the data, and then you might have a few outliers on the end. And then once again, this is what skewed left would look like. Also, I wanted to mention, anytime the graph is symmetric, like this normal distribution here, the mean, median, and mode are all generally the same. The mode is obviously the highest one, but the median, the middle numbers, are going to be at the same place. And the average is also going to be at the same place. But remember, if you have skewed data, especially if there are outliers, that pulls the mean drastically. So the mean gets pulled the most, the median gets pulled a little, which is why we use the median in this kind of situation. Imagine these are your test grades and you have a few zeros. That's going to pull your average way down. It would pull the median down a bit, but not quite as much as the mean. And then same thing on the high end. The mean gets pulled a lot with skewed data, and your median gets pulled a little. All right, so like on data like this, we should use the median, not the mean, because with skewed data, you don't want to use the mean. This one is not perfect, but it's pretty close to a normal distribution. There's no real skew on either side, so we've used the mean. This one is a little skewed right. There are some outliers over here, so we would not want to use the mean